In this video, we're going to look at concentration calculations involving hydrates, which cause complications in the concentration calculation itself. If we start by looking at the dissociation reaction of copper 2 sulfate pentahydrate, we know that an ionic solid dissociates into the two separate ions that make up the compound, in this case, copper with a 2 plus and sulfate with a 2 minus, when this compound dissolves in water. But of course, because this is a hydrate molecule, the water molecules that are associated with the ionic solid are also going to dissociate, and that means that these water molecules are going to become part of the solution. Now, this causes a problem for concentration calculations because that means that the solution volume is actually going to increase because of the water in the hydrate molecule, and this makes calculating ion concentrations a little bit more complicated. If we start from the beginning, our concentration calculation works exactly the same way as before, where we start with the mass of our solute, in this case copper 2 sulfate pentahydrate, and we need to figure out what the number of moles of this compound is in order to then divide this by the volume of the solvent in order to figure out what the initial concentration is. So let's start by calculating the molar mass of copper 2 sulfate pentahydrate. If we go to our periodic table, the molar mass of copper is 63.55, molar mass of sulfur is 32.07, and the molar mass of oxygen is 16. We also need the molar mass of hydrogen, 1.01, to calculate the molar mass of all of the water in the hydrate. So if we add everything together, molar mass of copper is 63.55, sulfur is 32.07, we have the molar mass of oxygen, which is 16, times 4 is 64, and the molar mass of hydrogen, we'll do water separately. Molar mass of hydrogen is 1.01, times 2 is 2.02, plus 16 is a molar mass of 18.02. If we then multiply this by 5, it comes to exactly 90.10, and if we work some quick arithmetic, we can find out what the total molar mass is. If you've done this correctly, the molar mass should come to 249.62 grams per mole, and that allows us to figure out what the number of moles of solute that we're operating is. Now, normally this would be an easy calculation, and we would just take this number and divide by 0.975, which is our solution volume in liters. However, the problem is this additional water, which is going to increase this volume here. So we need to figure out how many liters of water we are adding when this amount of solute dissolves. Well, we can figure that out by adding this additional calculation here. So to our initial volume of water, we're going to add the volume of water that we make here, which we can figure out by calculating the number of moles of water. So let's go ahead and do that. We start again with the mass of our solute, copper 2 sulfate pentahydrate, and then we divide this by the same molar mass that we calculated, which is 249.62 grams per mole. So that tells us the number of moles of our solute, and then for every 1 molecule of copper 2 sulfate pentahydrate, we have 5 water molecules. So what this tells us is the number of moles of water that we have, but of course we need to find out what the actual volume in liters of this is. So in order to do that, we need to multiply by the molar mass of water and then use the density of water that's given in the question here in order to find out what the volume of that water would be. So our molar mass of water is 18.02 grams per mole. so moles cancels, allowing us to find out the mass of water. And then here we can divide by water's density, which again means multiplying by 1 milliliter over 0.997 grams. This is the density of water. We can see here that grams cancels, leaving us with the number of milliliters of water that we would make. But of course, remember that concentration is always measured in liters, so we need to multiply by one more conversion factor, 1 liter over 1,000 milliliters, and that will give us, this long extension here will give us the volume in liters of the amount of water that we added through the dissociation of our solute itself. And if we take this large number and add it to the original solution volume, that tells us what the total volume of our solution is. And all that remains to do is take the number of moles of solute that we dissolved and divide it by this total volume that we have. If you put this into your calculator, this number comes to approximately 0.0228 moles of CuSO4, which is our solute, divided by the volume of water, including the small volume of water that we added when this compound dissolved. And again, normally we don't refer to our solute by the ionic solid because the two ions dissociate from each other. But again, because the ratio of our solute to each ion is 1:1, this number would be equal to the moles of Cu2 plus per liter, which is also equal to the moles of SO4 2 minus per liter. So in summary of everything, to make sense of all of these calculations, we start by writing the equation of our solute to see how it's going to dissociate, and recognize that we're going to add a small volume of water, which is going to change what the final solution volume is. From there, we can convert our mass of solute into moles, and then once we figure out the volume of water that we've added, we take that number of moles of solute and divide it by the total volume, including this volume of water that we added, giving us the solution that we've seen here. In the next series of videos, we're going to be focused on calculations involved with acid and base ionization reactions.